Up to now, for the most part, we've considered groups as sets with special multiplications. Now, we focus on the aspect of groups as symmetries of sets. To formalize the notion of symmetry, we use group actions. So definition. We'll have a group G, a set X, and we'll define an action of G on X. It's going to be a map from the product of G and X back into X. We'll denote it by pi of G applied to X, and it'll satisfy the following two conditions. Pi of E of X will be equal to X, and pi of G1, G2 on X is equal to pi of G1 on pi of G2 of X. Now, the first condition just says pi of the identity element is the identity map from X to itself. Second item says pi respects group multiplication. So if we have a product, I can multiply in the group, then apply it to X, or I can apply G2 and then apply G1, we get the same answer. For some examples, first, if we let G be equal to symmetric group on n letters, S sub n, I'll let X be the labels 1 through n. Then we just have the natural map. If I take any permutation, that's going to act on the label I just by taking the permutation evaluated at I. If we let our group be the integers under addition, we'll let our X, our set, be equal to the real numbers. Then we'll have an action by translation. So I'll let pi of n applied to X be equal to X plus n. So these are just going to be translations to the right or left of the real line by integers. Then we could try if I let G be equal to S1, the circle group. So I'm going to realize this is the unit circle in the complex plane. So we can write every element in the form e to the I theta. Our set X is going to be the complex plane. Then we'll have a group action by sending e to the I theta applied to Z equal to e to the I theta Z. So the effect here is just to do a rotation counterclockwise by theta of the complex plane about the origin. We have important examples of group actions where the set X is G itself, but we save those examples for later. Now, another way to think of a group action, instead, we consider it as a homomorphism pi from the group G into the group of bijections from X to itself. Now, at no point in the definition do we note that pi on G has to be a bijection, so let's show that. There are two ways we can go. First, we could show pi of G is 1 to 1 onto, and I'll leave that to you. Or we could just find the inverse map. Now, recall, if I want an inverse map, I'm just looking for another function. So if I compose pi G with that function in either order, we get the identity map. Our first guess should be the inverse to pi of G is equal to pi of G inverse. So let's show that. So we compose. If we apply pi of G to pi of G inverse on X, we could use property 2 to put everything under 1 pi. So you have GG inverse. That becomes the identity. And then pi of the identity is the identity map on X by property 1. Now, we show this in the other order using the same argument. So we have that pi of G and pi of G inverse are inverse to one another. So pi of G is a bijection. Note, it's crucial that we use that pi of the identity was the identity map on X. Okay, otherwise, it's not clear what we use for the inverse function. Now, we'll move into another theme for group actions. So if I have a group action, that's going to put an equivalence relation on our set X. So recall equivalence relation, same as putting a partition on X. Now, the relation that we use is just, can we get there from here? So I'll say X is related to Y, okay, X and Y in our set X, if there exists an element G in G, such that pi of G on X is equal to Y. So we want to show that this relation is reflexive, symmetric, and transitive. To show that X is related to X, I just set our group element to the identity. So that's straightforward. To show symmetric, we want to show if X is related to Y, then Y is related to X. So if X is related to Y, we have some G such that pi of G of X is equal to Y. By our formula here, we can push this to the other side to get X equal to pi of G inverse on Y. And then we just let our group element be equal to G inverse. So we have that Y is related to X. Then, for transitive, we want to show if X is related to Y, Y is related to Z, then X is related to Z. So we'll have, for some G and H, pi of G on X is Y, pi of H on Y is Z, and then we just compose. So we'll have Z equal to pi of H, pi of GX, and using property 2, we can put them under 1 pi, so our group element is going to be H times G. So we have transitive, and that makes our relation an equivalence relation. Now, because we have an equivalence relation, we're going to talk about equivalence classes. When we have a group action, the equivalence classes are called orbits. If I fix an X, the orbit of X is just going to be the set of all Y in our set X, such that X and Y are related. So if we follow out the definition, that just says, take your point X, then we're going to push it around by all elements of G, or translate by elements of G. If we get all of X back, so that means we pick any X, we push it around by all elements of G, we get all of X back, then we say the group action is transitive. Now, because we have an equivalence relation, the equivalence classes give us a partition of X. So that means I can write X as a disjoint union of the orbits. Let's look at our examples from before. If we have our group, symmetric group on n letters, with the natural action and the labels 1 through n, we have a transitive action. So if we consider the point 1, I can get to the point 2 by applying the 2 cycle 1, 2. I can get to 3 by applying the 2 cycle 1, 3, and so on. So we get to every other point from 1 using a 2 cycle. So transitive. If we use the example with the group as the integers, space as the real numbers, then this action is not transitive. So if I take any real number X, we apply all group elements. So we're just going to add and subtract all integers. Then our orbit looks like this. We have X, I keep adding 1 to X, and keep subtracting 1 from X. So not transitive. Finally, we have the circle group acting on the complex plane by rotations about the origin. If I fix some Z in the complex plane, then we apply all rotations. We're going to get a circle that goes through our point Z, centered at the origin. With the special case that if Z is equal to the origin, then that's its own orbit. Note here, this shows that all the orbits that show up in the partition need not look alike. Next, we consider orbits as cosets. For that, we need a definition. So we'll fix some X in our set. Definition, stabilizer subgroup of X in G is defined as all G in the group, such that pi of G sends X back to itself. So stabilizer, because we want all elements in the group that leave X undisturbed. Now, we'll show the subgroup property, but we note stabilizer need not be normal. So if I let G be the symmetric group on 4 letters, X equal to 1, 2, 3, 4, we have the usual action. Stabilizer of 1 is going to be isomorphic to an S3. And that's on the labels 2, 3, and 4. So not normal in S4. Now, for the subgroup property, we need to show closed under multiplication, closed under inversion, and non-empty. We get non-empty by showing the identity is in our subgroup. So let's suppose closed under multiplication, we have G and H in the stabilizer of X. I want to show that G times H is also in the stabilizer. So we'll take pi of GH on X. I use property 2 to split it up. Then by assumption, pi of H on X is X. And we have pi of G on X is also X. So that shows pi of GH on X is X. And GH is in the stabilizer. So close under multiplication. Show non-empty. We have pi of the identity on X is equal to X by property 1. So we have at least the identity element in our subgroup. Then for close under inverse, so I want to show if G is in the stabilizer, G inverse is also in the stabilizer. So by assumption we have pi of G on X is X. We use our rule for the inverse function from before to push pi of G to the other side as pi of G inverse. So that shows that G inverse is in our stabilizer. So closed under inversion. So that shows we have a subgroup. Now, for examples, if I take S sub n acting on 1, 2 through n, stabilizer of any label I, it's just going to be isomorphic to an S sub n minus 1. So we're just going to take all of our labels and we're going to throw away I. For translations of the integers acting on the real numbers, here, if I fix some real number x, the only way I can translate to get back to x, so I'm going to leave x undisturbed, is by translating by 0. So we have only one element in the stabilizer here. If we consider the circle group, we'll have two cases. If I have an element z, okay, not equal to the origin, then the only way I can rotate that point and make it stay where it is if we just rotate by the angle 0. So in that case, the stabilizer is the point 1. Otherwise, if I'm at the origin, then every rotation stabilizes the origin. So we get the whole group back. With the definition of stabilizer, we can now state the following proposition. We have the cardinality of the orbit of x is the same as the cardinality of the left coset space G mod the stabilizer of x. To show this, we need to produce the bijection between the orbit and the coset space. The natural candidate is to use Q going from our group to the orbit. I'm just going to send G to pi of G on x. So it's going to take x and translate by G. Now, show that this descends to a map on the cosets, I have to show if we replace G with G times H, where H is in the stabilizer, okay, for notation, we'll call that capital H. I want that Q of GH equals Q of G. So we could change G on the right by any element in the stabilizer. Now, let's just check that. So if I take Q of GH, we have pi of GHX by definition. We split that up by property 2. Then pi of H on X is just X because H is in the stabilizer. So we get pi of G on X, which is Q of G. So that's our assertion. Now that means I have another map, Q tilde, on our left coset space going to our orbit, defined by Q tilde of the coset GH is equal to Q of G, which in turn is equal to pi of G on X. The way to think of this, if I stick an element of the stabilizer in here, it's going to have no effect. Now, this is the bijection. So I want to show Q tilde is 1 to 1 and onto. To show 1 to 1, if I take two cosets, GH and HH, we apply Q tilde, set them equal to each other. We want to show these cosets are equal. So by definition, I have Q of G equals Q of H, or pi of G on X equals pi of H on X. I could push pi of H to the other side, put everything under 1 pi. So we have that pi of H inverse G on X is equal to X. So H inverse G is in the stabilizer of X, which says that G is in H stabilizer of X. So that means the coset GH is equal to the coset HH, and we have 1-to-1. For onto, if I have some y in the orbit of X, that means there's some G such that pi of G on X is equal to Y. So I'll just take Q tilde on the coset GH. That's equal to Q on G, which is equal to pi of G on X, which we have by assumption is equal to Y. So I can find some G that maps to the point in the orbit Y. So onto. Let's finish by checking our examples. First, we have S4 acting on 1, 2, 3, 4. We know the action is transitive, so the orbit of the point 1 is going to have 4 elements. The number of elements in S4 is 24. The number of elements in the stabilizer of 1 is equal to 6 because it's isomorphic to an S3. So we have that 4 is equal to 24 divided by 6. If we consider the integers acting on the reals by translation, I fix a real number x, then its orbit is just going to be x plus the integers. So this is a countable set. If we take the coset space, z mod 0, this is also going to be countable. So that checks out. If we take S1 acting on the complex plane, we have 2 cases. If z is not the origin, then our orbit's a circle, so its cardinality is uncountable. For the origin, cardinality of the orbit is just going to be equal to 1, because we have 1 point. Now, if we take quotient of S1 by the stabilizer, when z is not 0, stabilizer is just the point 1, so we have uncountable. If we consider the origin, then the stabilizer is all of S1. So we have S1 mod S1, and we have cardinality 1. So that checks out also. Now, for an example with a little bit more going on, let's consider the action of D8 on R2, so the plane. Here, the action is just going to be the action on the plane induced from the action on the square. Okay, we orient our square like this. Now, the different cases that we have, if we use the origin, then stabilizer is going to be all of D8. Our orbit has 1 element. The coset space has 8 over 8 elements. So that checks out. If we consider the point 1, 1, okay, the stabilizer here is just going to be the identity and the element that switches 2 and 4. So we have 2 elements. Now note, the orbit of 1, okay, well, what can we do? If I flip in this line, nothing happens. If I flip in this line, 1 goes to 3. If I flip in this line, 1 goes to 2. If I flip in this line, 1 goes to 4. We're only going to have 4 points in the orbit. So we have 4 equals 8 divided by 2, and that checks out. If we consider 0, 1, same idea as here. Stabilizer at this point is going to be the identity and the element of order 2, 1, 2, 3, 4. So that's just going to be the flip in the y-axis. So we have 2 elements. And again, 4 is equal to 8 divided by 2. Final case, I'll take the point 1, 2. So we're going to go over 1, up 2, and get this point. If we reflect through this line, this point goes to here. If we reflect through this line, this point goes to here. And you'll note, when we do all possible reflections, we're going to wind up with 8 points. Now, that means, okay, if we think about this point here, stabilizer is going to be only the identity element. So that means we have, in terms of the orbit, Number of elements in the orbit is 8, which is the same as 8 divided by 1. So that checks out.